Now if we have a mass little m much less than mass big M, with the mass little m in a circular orbit around mass big M at radius r, then we know that the velocity of the orbit is the square root of big G big M over r, obtaining that just by setting the expression for the Coulomb acceleration, for the gravitational acceleration equal to the expression for the centripetal acceleration. Okay. Now, if we have this object in circular orbit, and I've drawn the circular orbit here again, mass big M, little m, radius r, here's our circular orbit. Now, at some point in that circular orbit, we deliver an impulse over a short period of time, impulse f delta t, we get a delta v. Now, this should be actually an f net, but I'm not going to make that. Actually, maybe I am. That's something that's important to keep reminding ourselves of. That's an F net. That's an F net. That little smudge down there is a net. Okay, we have an impulse that gives us a change in velocity equal to the impulse divided by the mass of the little object. So that after the impulse, the velocity attains, the object attains a new velocity, and there's a change in kinetic energy. It's equal to 1/2 the mass times final velocity squared minus initial velocity squared. Of course, that factors into u minus v times u plus v, u minus v being your delta v, u plus v being the sum of the two velocities. Okay, now that's not particularly important for the development we're going to do here, but it's worth keeping in mind for later applications. Okay, so we do this, and the object is happily moving in a circular orbit. We suddenly bump it. What's it want to do? It wants to fly off in this direction, but of course the mass here attracts it, and it doesn't immediately deviate a lot from its circular orbit, but it does get more energy, too much energy to have the velocity that keeps it in a circular orbit, and it starts moving outward and goes into an elliptical orbit that turns out to come back to the same point. And we could prove that it has to come back to this point, but we're not going to do that just now. Okay. Now, in that elliptical orbit, as it moves from here to the greater distance here, what's happening to its potential energy? It's gaining gravitational potential energy because it's moving away from the direction of the force. Okay, so it's moving away from the force, gradually moving away. Now let's look at how that works. Okay, in a circular orbit, you have velocity tangent to the circle and net force perpendicular to that velocity, because the net force is back toward the center, and the velocity being tangent is perpendicular to the radial line. Then, in that case, no work is being done on the object because the force is perpendicular to the displacement over any interval of time. So there's zero work being done. In an elliptical orbit, that's not the case. In an elliptical orbit, at this point of the ellipse, the velocity is not perpendicular to the net force. The net force is still back toward the center, but the velocity is now out away from a perpendicular to the net force. And it should be obvious. We could do a geometric argument for that. But if the orbit was circular at this point, the velocity would be perpendicular to F net. The orbit is not circular. It's at this time an angle was circular, so the velocity is not perpendicular to the net force. And the velocity and the net force, the component of the velocity in the direction of the net force is in the direction opposite the net force. So the net force is doing negative work on the mass, which is going to decrease its kinetic energy. Now, in an orbit, we assume we're out in space. There's no drag. There are no non-conservative forces. So any change in kinetic energy is accompanied by an equal and opposite change in potential energy. Now, that's not true while the impulse is being delivered, because here there's a non-conservative force acting. but as soon as the impulse is over, it's all conservative forces. The only force acting is the force of gravity. Okay, so we can see here that the velocity is going to have a component in the opposite direction of the net force, so that the net force is going to be doing negative work. And that's going to continue all the way out to here. Then when you start moving back closer to the planet, we have the situation where the velocity is in this direction, net force in this direction, and the angle between them is acute. The velocity will have its component in the direction of the net force, so there's going to be, on any short interval or in any time interval, a displacement in the direction of the net force, so that gravity is going to be doing positive work and increasing the kinetic energy. So we have decreasing kinetic energy as we move out, increasing kinetic energy as we move back to our close point. So we have what's called the perigee, the close point, the apogee, which is the far point, and the apogee really should be diametrically, or should be along a line from the perigee through the center. So they need to be at opposite positions along the orbit, and I didn't draw it that way, so it's kind of a flawed drawing, but you still get the general idea of how energies are changing. Okay, so now we understand this much about an elliptical orbit. It can be accomplished from a circular orbit by an impulse parallel to the direction of motion at any time. Kicks us out into an elliptical orbit where the velocity gradually decreases, and then the velocity increases, and we come back to our original point, and we keep going through that orbit.